Welcome to students. So, today we will be formally looking into definition of topological entropy, and especially today we will be looking into Adler's version. So, this is basically this definition is due to R. L. Adler, A. G. Cohen and M. H. McEntrew. And this was defined the year 1965. So, what is this definition all about? So, again let us go back to what are our assumptions. So, our X D is a compact metric space, and our X F is a dynamical system. Now, the feature for this definition of entropy is that it basically depends on the compactness of the phase space. So, though metric is not required here, metric does help us in sorting out some properties of this entropy, but this is basically used whenever you have a compact space and that is not metrizable. This becomes very handy in trying to compute the topological entropy. Though if you look into per se the definition, it appears to be a little bit cumbersome to try to compute the topological entropy from this definition, but it very well shows us what is the structure and what is the reason what behind the topological entropy, how the entropy evolves. So, that is very nicely displayed by this particular definition. So, since we have already assumed compactness, let us look into this definition. So, you all are very familiar with properties of compactness, and that is what we are going to use here. So, let U be an open cover Now, we very well know that an open cover will always have a finite subcover because of compactness, and hence we let Nu be the minimum cardinality of a subcover of U. So, try to take the minimum possible subcover of U, and the minimum cardinality is something which we denote as Nu. And then we define H of U, capital H of U, to be log of Nu. Now, let V be any other cover. So, let V be any other open cover then we say that V refines U if, and we write it as so V refines U if for every V belonging to V there is a U in U such that V is contained in U. In particular, if your V is actually a proper subset of U, right, and it is a subcover of U, then we can say that V refines U. So, proper subcover will always refine the open cover. So, for any two open covers we can see whether we are looking into, so we can have a class of open covers of X and then we are looking into basically the chain which comes up from refinement. There is also another way of defining refinements. So, say given any two open covers, U and V, we define the join. So, we define U join V, basically this is the join of U and V as a cover consisting of all non-empty sets Ui intersection Vj with Ui belonging to U and Vj belonging to V. So, you take all U's from U, V's from V, intersect, take all the non-empty intersection, take that collection will again be an open cover and that open cover will be a refinement of both U and V, right, because for everything there will be something containing that, right, some set in U containing a set here, some set in V containing a set here. So, you will get a refinement. So, this is one of the ways of creating a refinement. Now, if we can define a join for any two open covers, we can similarly define a join for any finite number of open covers, right. So, we can similarly define so, we have this process of joining and this joining gives us refinement. Now, here we want to note something. If you look into U, right, U is already an open cover. Now, we define Fu to be basically the set of all Fu such that U belongs to U. Now, think of that, because our F need not be open, right, need not be an open map, right, this Fu need not be open, but still we can define Fu, right, the Fu will cover X, fine. Now, since Fu covers X, we can think of that, we can think of the minimum cardinality of this cover Fu, of a finite subcover of this cover Fu, and what we find here is that n of U, right, would be same as n of Fu, and maybe take this Fu, and basically that implies, I think I have not defined n here. So, maybe I can just go back to this sometime later. Okay. I think we have defined nu here. So, start with nu, right. So, I am just going back to this factor that n of u will be same as n of f of u, and that happens to be, since this is same, right, we can say that h of u, right, going back to this definition again, h of u is log of n of u. So, h of u happens to be same as h of f of u. For any open cover u, right, all we know is that h of u will be same as h of f u. What happens here next is that look for a cover. So, let u be a cover of an open cover of X. Now, for an open cover of X, right, we know that f inverse u, right, which we can define it as F inverse u for all u in U. This is also an open cover of X. Now, it is quite possible that the sets F inverse u, right, they are larger than u. So, in that sense, if I am looking into this as an open cover of u, right, and if I am looking into a finite subcover by F inverse u, it is quite possible that the minimal cardinality, right, of the finite subcover of F inverse u will be less than the finite cardinality for u, right. So, what we have here is that n of F inverse u, right, will be basically less than or equal to n of u, and in that case we can simply say that h of F inverse u will be less than or equal to h of u. Now, what we need is the fact that F inverse u is also an open cover, and you start with u to be any open cover, F inverse u is also an open cover. Since F inverse u is also an open cover, F minus 2 u, right, F inverse square, right, minus 2 u is also an open cover, right. Similarly, F minus k u is also an open cover for any k, any positive k, right. So, what we find here is that we can define, right. So, we define u capital N to be basically the join of u F inverse u F minus n u. So, these are basically n plus 1 joining of n plus 1 open covers, but we define this to be this join. So, we know that a join will anyway be a open cover. So, join gives you an open cover, not just gives you an open cover, it is basically a refinement of all these open covers. So, it is a refinement of u also, it is a refinement of F inverse u also, and so on. So, it basically gives an open cover of X which refines u. So, mostly we are interested in refining u. So, un is an open cover of X which refines u. We will look into this lemma. So, for our dynamical system Xf, or let me just assume that let Xf be a dynamical system, and let u be an open cover since we are interested in taking up, anyway we are interested in taking a finite subcover, we are only interested in the finite subcover. So, we can very well assume that u itself is a finite open cover of X. So, let u be a finite open cover then the sequence. So, we are looking into this sequence, I am looking into the sequence a n, where what is my a n? My a n happens to be h of u n, right, where u n is just the join that we have defined. So, if I look into this sequence satisfies the subadditive law So, subadditive law is a m plus n is less than or equal to a m plus a n for all m n greater than or equal to 1. So, h of u n satisfies the subadditive law and hence has a limit, hence this limit. So, I am defining small h of u to be equal to limit as n tends to infinity 1 upon n times h of u n, this limit exists. Now, we already know we all need to prove. So, to prove this lemma basically we all need to see is that your h of u n satisfies the subadditive law, right. Then we are just applying the property of subadditive sequence, right, to show that this limit exists. We go into the proof here. So, we note that for open covers u and v your n of u join v is less than or equal to n of u times n of v. All we know how do we define u join, right. So, we are just intersecting one element of u and one element of v, and now we are saying that okay fine, when we have a subcover from this join, right, well, how many elements can we have, how many minimum elements can be there, right. So, that will be always be less than or equal to the minimum, the multiplication of the minimal elements that you get from the previous two. So, this is very trivial to observe here, and hence what can you say about the join of h and u? So, if I look into the join of h and v, this is basically log of n of u join v. So, n of u join v, this is less than or equal to, again I can think of log of nu times nv. So, this is log of nu plus log of nv, and this happens to be your h of u plus h of v. So, if I take a join, right, we definitely see that this satisfies this property. So, what happens in case of a finite thing which we are more interested in, right. So, let us look into what happens to our a m plus n. Can say that. So, what is a m plus 1? That is basically h of u m plus n. Now, we know what is u m plus n, right. It would basically be h of, right, I have u join f inverse u, right, join, I can go up to f minus n u, join f minus n minus 1 u, right. Fine. I am looking into h of these joins, and again if I look into that factor, right, look into what is this quantity. I am just looking into what is this quantity. This is just u n by definition, and now I am looking into this quantity. What is this quantity? I can say that this is f minus n of u m. I am looking into this complete join, but what is this complete join? It is basically the join of this part and the join of this part, right. So, the first part is just u n, and the second part happens to be f minus n of u m. So, we can say that this is nothing but this is h of u n join f minus n of u m. Now, we just apply what we have previously seen. If I have two covers, right, h of u join v is less than or equal to h of u plus h of v. So, this is less than or equal to h of u n, right, plus h of f minus n u m. Now, think of that, we have already seen that for any cover u, h of u is same as h of f u. We have already seen that. So, we apply this here to f n, right. So, this would be same as h of u n plus h of f n of f inverse of u, u m, right. So, this happens to be same as h of u n plus h of f n of f minus n of u m and this is nothing but h of un plus h of un. So, we know that this h of un is nothing but our am, right, plus am. So, h of un satisfies the subadditive law, right, and hence we can say by subadditivity limit n tends to infinity, h of un, right, this is equal to hu excess. We are formally defining an entropy now. So, I am defining h t of x, which I can also write as h t of x f, right, which is basically the supremum of h of u such that u is a finite cover So, since I know that my HU is defined, HU always exists, HU is defined, you can take these numbers HU and you define the supremum of these numbers HU. So, the supremum of these numbers is denoted as HTX or HTFX, and this HTFX is a non-negative number, right. Since we are taking supremum, this is a non-negative number. And HTX is called the topological entropy my HTX is again supremum, right. So, it can be in the extended real plane also, so it can be infinite also since it is the supremum. So, my HTX basically you can say that HTX belongs to R plus union infinity, and this is basically my topological entropy. As we have already seen this fact that topological entropy being positive, right, is a sign of chaos. So, let us look into a proposition here. So, let XF be a dynamical system of course, our X is compact here. Then we have two facts. If YF, so we are taking a subset of X, YF is a subsystem of XF. Then the topological entropy of Y will be less than or equal to the topological entropy of X. And the second fact here is that if I have a factor here, so XF is factoring into YF, this is a factor, then again the topological entropy is less than or equal to topological entropy of X. So, by taking a factor we are always reducing the entropy, and if you try to look into the proof of this is simple in the sense that we know that when we are taking a subsystem, right, if you take any open cover of X, right, that will also be an open cover of Y, you can think of that as also as an open cover of Y, and then the minimal cardinality may decrease, right, and hence you will get that the entropy will be less, right. And similarly happens for a factor, because if you try to look into a factor, take any open cover of Y, right, take phi inverse, that will be an open cover of X, right, and it is quite possible that the minimum cardinality here will be less than the minimum cardinality here, because we will have other open covers of X also, right. So, we are taking supremum over more number of elements, right. So, the entropy may increase here. So, this is a small proposition, but of use is another proposition which we shall see right now. So, we take another proposition here. So, now I am taking a chain of refinements. So, I have U1, right, it is refinement U2, this is refined by U3 and so on. So, this is a sequence of open covers. With now here we need a metric space, we need our X to be a metric space here, because we are going to define the diameter of an open cover. So, with the diameter of cover, so I am defining diameter of UN to be the supremum of diameter U such that U belongs to UN. So, the maximum, the supremum of this diameter of all elements of U, that forms the diameter of the open cover, and we are taking this sequence of refinements in such a manner that the diameter of UN is converging to 0. So, of course, this is with respect to supposing I have such a sequence of open covers, then the topological entropy HTX is nothing but it is limit as n tends to infinity of H of UN. So, basically we can call H of UN to be the entropy of the open cover, right. So, entropy of the open cover, if the open cover is basically decreasing, right, you are looking into a decreasing sequence here, then you can say that the entropy happens to be limit of this UN. And the proof here is actually very simple, but it is a nice idea here. So, try to look into the proof here. So, let V be any open cover. Now, we know that our X is compact, we are in the metric space setting. So, every open cover will have a Lebesgue number. So, we define take delta to be the Lebesgue number. For V. So, this is the Lebesgue number for V. Now, what we are taking is, we know that this is a decreasing sequence, diameter is tending to 0. So, somewhere the diameter will tend to be less than delta. Somewhere the diameter of the open cover, there will be some n onwards such that the diameter of UN will be less than delta. So, which delta is the Lebesgue number of V. So, we know that UN is basically UN refines V for every n with diameter of UN, right, less than delta. So, that means now you take any open cover, what you find is that your U from some n onwards, your UNs will always, all the UNs will always be refining this cover, right. So, all we need is, we just need that what is this cover. So, your H of UN happens to be a decreasing sequence, right. So, H of UN, so the entropy of UN, right, is a decreasing sequence. Obviously, since un is decreasing, the diameter is decreasing, right. So, the h of un will be decreasing, right, and since h of un is decreasing, we know that h of un refines everything and this is a decreasing sequence. So, since this is a decreasing sequence, we can think of that since this is a decreasing sequence. So, you will always have this will tend to a limit, right, and that will be our topological entropy, because our topological entropy is the supremum of all covers, right, the supremum of the entropy of all covers. But here we have a decreasing sequence of open covers such that take any open cover, it is going to be refined by this open cover, this one elements of the sequence, and hence your entropy of x. So, I can say that hence entropy of x is limit as n tends to infinity h of un. Now, this is actually a very important idea, because this helps us in trying to compute entropy for many things, right. And though the definition, of course, this requires a metric definition, but this definite the benefit of this definition is that this definition can be used for all compact spaces which are not metrizable. As we shall soon see, this is another definition of entropy due to Bowen, and that definition is practically more useful than this particular definition. But if you want to use a definition using open cover, right, in a metric space setting, this proposition is very helpful in determining the entropy. So, let us try to take up some examples for this finding out entropy using this method, and that will give us a better idea of how to use this definition. So, we look into our first example here, and since we have already discussed the full K shift, right, in the previous lecture, we will similarly discuss the full K shift here, and we will try to compute the entropy using this definition. So, for the full K shift, take any n, any natural number, then what we have is we have Pn, which I am defining as a disjoint union of all the words in Bnx, right, or this. Now, what is my element? My element x is in X such that if I take this block x from 0 to n minus 1, so this happens to be W. We know that there will be different words, B and X will have different blocks. So, we are defining the blocks in this particular manner. We know that this forms a partition of X. So, Pn gives a partition of X, is a partition of X into Clopin sets for all words So, whenever you take fix any n, right, you know that you will have words of length n, and that gives you a partition of X into Clopin sets, because these all will be cylinder sets, right. So, this gives a partition for partition of X into Clopin sets. Now, for this partition we define U n m to be the join, I am taking I going from 0 to m, right, sigma minus I of Pn. So, start with the partition n Pn, right. So, this is basically, this is again an open cover of X, you can think of Pn to be an open cover of X. So, this is an open cover of X, and for this open cover, right, we take this, we define Un m. Now, we know that this is also going to be an open cover. What is H of Un m? We know that this is going to be sorry, I should not say H, I am looking into N now. What is N of UNM? So, basically what is the minimum number of elements in UNM which can cover your X, right. So, looking into the minimum cardinality here for this open cover. So, we find that this is going to be Ln, right, where your Ln happens to be cardinality of Bnx. Think of that. Take U n n, right. Then we know that U n n will be refined by U n plus 1 n plus 1. I am taking a words of length n plus 1, right, and I am looking into a bigger refinement there. So, that will definitely refine U n n for all n greater than equal to 1, and so this forms a decreasing refinement. So, now I have a decreasing refinement, and what can we say about the diameter? The diameter of UKK, right, as your k increases, this is tending to 0, because as you increase the number of words, right, what happens when you increase the number of words? What will be the diameter? Because any two elements in that, basically in any partition, any two words will be very close to each other, right. So, the diameter is basically going to get smaller and smaller. So, this diameter converges to 0. So, diameter of UN, so I should say UK, right, that is tending to 0. So, what we find here is a decreasing refinement with, let me mark this part also, with diameter of UKK, right, tending to 0 as k tends to infinity. This is tending to 0, and that gives us that the topological entropy of X, right, can be very well given as a limit of the entropy of UNN. So, we think of this part that the entropy of X, right, is nothing but limit as n tends to infinity. I have h of u n n. Now, if I look into h of u n n, right, what is that equal to? So, this is nothing but this is limit is n tends to infinity 1 by n times h of u n n. But if you look into that factor, this is nothing but limit as n tends to infinity 1 by n log of n u n n, and what is n u n n? That is ln, right. So, this is nothing but this is limit as n tends to infinity 1 upon n, right, log of ln, which we know what is our ln. This is limit as n tends to infinity, right, 1 upon n log of mod of b n x, and this is what we had discussed in the previous case, right. This is basically, this gives the number of distinct orbits, right. The definition that we had taken up, right, it is same as this particular definition. So, we are looking into this part 1 by n log of mod b n x, and now if our x is the full k shift, right. So, if x is the full k shift, we know that this will tend to be equal to log of k, because then your b n k will be k to the power n, right. So, b n k happens to be, so b n x happens to be k to the power n, right, in that case. So, this entropy will turn out to be log of k. So, for the full shift, for the full k shift, right, the entropy, topological entropy turns out to be log of k. So, this is basic, this is the basic idea of entropy that we had used in the previous class. And now I just want to look into one proposition here. For the dynamical system Xf, if F is a homeomorphism, then the topological entropy of Xf is same as the topological entropy of X F inverse. Now, this is very helpful in computing entropy, and one can easily see this holds true because if you try to look into, so the hint here is simply that the fact that if you try to look into h of un, right, it will be same as h of f of n un, right, and h of f of n un can be written as, now you are trying to compute that part, right. So, it is written as h of, you now have f n of, this is u join f inverse u, right, join f minus n u, right, you have this join here. And if you try to look into that part, this is nothing but this will give you h of f n u, right, join f n minus 1 u, right, join u, which is nothing but this basically gives you the entropy of. So, this is, since this is same, right, you compute the entropy here 1 upon n times this factor, right, what you get is the entropy of f inverse, right. So, this is basically the hint here, and we observe that this result is only true for a compact X, it is not true otherwise, because otherwise you can take, say, take the positive real line, take the mapping to X, then the entropy of 2x on the positive real line happens to be log 2, but if you take the inverse there, the inverse is x by 2, which is a contraction, and for a contraction we know that everything, all orbits are tending to 0, right. So, the topological entropy there happens to be equal to 0. So, this is not true there. We will now look into another example of a system which we know very well, and we will see that topological entropy can also be equal to 0. There are cases where topological entropy can be infinite, right. The examples there are highly complicated. So, that is those examples, we will not be doing those examples in these lectures, but you have many systems for which the topological entropy is infinite. So, our example is again our irrational rotation. Now, we want to say that if I look into the topological entropy of this irrational rotation, this is equal to 0, and we try to prove this fact again using our Lebesgue number. So, let delta be the Lebesgue number. So, you start with the Lebesgue number, you start with an open cover, start with the Lebesgue number. What you are now doing is, you are taking points x1 up to xk, right, take this points in S1 such that your this arcs xi plus 1, if you will try to look into this particular arc, right, this particular arc has length, right, less than delta. So, you are taking any k points on S1 such that this length has, this arc has length less than delta. Now, you take V to be a refinement. So, V take V to be the union of all such arcs, then V happens to be a refinement of U. So, if I take V to be basically the union of all these arcs, is a refinement of U. Now, let us try to compute the entropy of this open cover V. Now, if I try to look into V, right, I am just looking into what is the diameter of V. So, the diameter of V, right, is going to be less than delta. Now, what happens here is you try to take the diameter of, so you take V join say T alpha inverse V, take V join T alpha inverse V, then what you get here is, we know that this is an isometric rotation, T alpha is just an isometric rotation. So, you are only going to rotate these arcs, right, in some particular angle. So, the number of points, right, where it is going to, so the number of points, fine, where this intersects. So, you will have at least one point in between xi and xi plus 1 where one of the image will be intersecting. So, what you have is you have like you had k points now, in the next turn you have 2k points, right. So, you will find 2k points and now you are taking the partition of S1 with 2k points, right, and again the diameter is anyway going to be less. So, it is going to be definitely less than delta, diameter is decreasing there. So, now you have 2k points. Now, when you take another, you take a join with T alpha minus 2V, right, you find that the join happens to be of, say you will find 3k points there, right. So, you find 3k, you find that you will find that these are 3k points. So, if you take up any say Vn, right, then in Vn how many points do you have here? So, you have basically a partition of S1, right, with nk points, at the most nk points. Now, with at the most nk points, what is the diameter turning out to be? You have at the most nk points, right, and the diameter there, this is less than delta. So, the diameter is again decreasing, right, delta, and then we have decreased delta by something. So, what you find here is that if I want to take h of Vn, right, this is basically going to be less than or equal to log of nk times, of course, I can think of it delta, right. So, log of nk delta, this is less than or equal to this particular fact, and if I try to look into 1 upon n times this factor, right, then 1 upon n times this factor is going to tend to 0 because 1 by n log n. So, 1 upon n, since 1 upon n log n is 0, right, it basically tends to 0 as n tends to infinity. So, what happens here is that if I take h of Vn, right, this will be less than or equal to log of n k delta, right, this is log or less than log of n k delta. So, this is basically going to tend to 0 as your n tends to infinity. So, again if I take this limit of h of un, right, that is tending to infinity, that is going to be 0. So, you have lot of zeros there, right, and this is a refinement of almost any open cover that you take up, you can find such a refinement, right, you will find some un because this is the diameter is decreasing, you find that this is going to be tending to 0. So, what you find here is that your entropy of S1, right, under T alpha is basically 0. So, you can take this open cover definition and you can show that basically if you take any, in fact this is true for any isometric stuff. So, if you take any homomorphism on a compact space X, you have a homomorphism, you can show that this homomorphism is isometric, right, then the entropy turns out to be equal to 0. So, the entropy in this particular case for an irrational rotation, the entropy is 0. In fact, if you start with a finite set, right, and we can take any permutation on the finite set, if that is our dynamical system, then again we know that the entropy is going to be equal to 0. Though we will see this that entropy does imply some some other definitions of chaos, but it is not true that all chaotic things that we have seen in the previous definition would turn out to be having entropy positive. Positive entropy is also a sign of chaos because it shows that there will be a multitude of orbits that you can see in the dynamical system. So, in the next class we will basically look into another definition of entropy, which turns out to be, because it is more useful, it is a metric definition, turns out to be more useful, it captures many other features. I hope this is clear as far as this is concerned.